Unit Operation Classroom. Today we are discussing a very important topic, wet bulb temperature estimation from humidity. My name is Shekhar Bhattacharjee. Vapor pressure data for water at various temperatures are given. We'll come to this later on. And air water vapor mixture at 100 kilopascals, approximately one atmosphere. One atmosphere is equal to, 101.3 kilopascals. So this is approximately one atmosphere with a relative humidity of 20%, has a dry bulb temperature of 310 Kelvin. So let's say we have a room here, and here the temperature is, so this is T dry bulb, which is the actual measured temperature. 310 Kelvin is approximately, let's say, 37 degrees Celsius. And the relative humidity is 20%. Okay. So that automatically gives you what's the value of partial pressure of water vapor here, and that gives you the value of humidity. We'll see how to do that. So the other data are given, like specific heat, latent heat of vaporization data are given. So we have to find out the wet bulb temperature. So the problem is the dry bulb temperature, or the actual temperature which is measured, is given. The pressure is given, which is 100 kilopascals. And the relative humidity is given. We have to find out what is the wet bulb temperature. What is the utility of the wet bulb temperature? Knowing the wet bulb temperature, we'll see later on. So first we'll see how to calculate the value of the wet bulb temperature given the dry bulb temperature, that means the actual temperature which you measure with the thermometer, and the relative humidity of the air in this room or in an environment or in an enclosure. So the given data, the total pressure P is 100 kilopascals, approximately one atmosphere, not exactly one atmosphere. Dry bulb temperature is 310 Kelvin, relative humidity, and we have to calculate the wet bulb temperature. First, what is the first step? That we calculate the partial pressure of water at this wet bulb temperature. That means here we have the dry bulb temperature is given and the relative humidity is given. How do we calculate the partial pressure of water vapor? So here what we have air plus dry air plus water vapor, right? So we have to first find out what is the partial pressure of water vapor here. And of course, what will be the partial pressure of air? So if we add these two, that will be, of course, the total pressure, right? Which is equal to 100 kilopascals. So depending upon the value of the relative humidity, we would be able to calculate what is the value of the partial pressure of water. So how to do that? So relative humidity is defined as the partial pressure at the dry bulb temperature, which is 310 Kelvin. Saturation vapor pressure at saturation pressure, that means the vapor pressure at the same dry bulb temperature. That means the 310. If the temperature, if the temperature 310 Kelvin, if this would have been totally saturated with water vapor, then what would be the vapor pressure? That is this value here multiplied by 100. Okay, so how do you find it out? So at 310 Kelvin, from the table, we'll find out that this value is 6.40 kilopascal. We'll see here that at 310 Kelvin, this is the temperature in Kelvin, and this is the vapor pressure water in kilopascal. So at 310 Kelvin, which is the dry bulb temperature, we see the saturation vapor pressure 6.40 kilopascals. So we can calculate the partial pressure of water vapor at that in that room or in that enclosure is equal to 1.28 kilopascals. So that is the first step. So here in this room, so as we said, this is the dry bulb temperature and the partial pressure of water is 1.28 kilopascals. What is the next step? Based on this value of 1.28 kilopascal, we should be able to calculate what is the humidity, because we know the definition. We can calculate that from the definition of humidity. The definition of humidity is given as, so there could be two types of humidity. One is a molar humidity and one is a mass humidity. So mass humidity is mostly used in calculation, and this is the standard SI unit. But in this problem, we don't need to do that. So we are not going to use the mass humidity. We'll just calculate the molar humidity. What is the molar humidity? It's the partial pressure of water vapor, which we have calculated right now, 1.28 kilopascal, divided by total pressure minus the partial pressure of water, which is the partial pressure of air. Right. So this is the ratio of partial pressure of water divided by partial pressure of air. And we know at the same temperature, the ratio of partial pressure will be equal to the ratio of moles. So this is equal to, in the room, we have 0.01296, very small moles of water vapor per kilomole of, if you take the kilomole of water vapor per kilomole of dry air. Okay. So this is the molar humidity. So what will be the next step? In the next step, we used the energy balance equation for adiabatic saturation temperature. We use that to calculate the wet bulb temperature. This is given in any standard textbook, so I'll just refer to any standard textbook, like let's say McCabe, Smith and Harriet, or Gene Complex, or any other book, and show your university or college lecture notes. So this is the standard equation for energy balance equation. This is the humidity at the dry bulb temperature, which is at 310 Kelvin. And this is the humidity at the wet bulb temperature, right? If you see and look at the concept of wet bulb temperature here, if we remember that wick here. So here, here the humidity, of course, here the air is saturated with water vapor. So at the wet bulb temperature, this is the saturation humidity. So at the wet bulb temperature in the wick here, this is the saturation humidity. Please refer to your textbook. Okay, so this could be found out if we know if we have to find out the wet bulb temperature, or if we assume a wet bulb temperature. So we'll find out the partial pressure of water vapor by assuming this to be saturated. So at the wet bulb temperature, we'll find out what is the saturation vapor pressure, or saturation pressure, or the vapor pressure of water, and from there we should be able to calculate the humidity at the wet bulb temperature. And this is the dry bulb temperature. This is the CP and lambda. What is the CP? CP is the molar heat capacity. The molar heat capacity at this temperature, per unit temperature, Kelvin here. So this is 0.035 given as kilojoule per mixture of water vapor and dry air. Let's look at the definition here. It says the specific heat capacity of air and water vapor mixture is 0.035 kilojoule per kilomole Kelvin. So here, this value is 0.035 kilojoule per kilojoule per mole of water vapor air dry air mixture Kelvin. But we have to make an assumption here, since this amount is very small compared to the dry air, because we have seen the humidity is very, the value is 0.01296 moles of kilomole of water vapor per 1 kilomole of dry air. So this amount is very small. So we can essentially say that this CP is equal to 0.035 kilojoule per mole of dry air. We are assuming this to be very small, Kelvin. Okay. And this is the molar latent heat of water vapor, which is 44 kilojoule per mole of water vapor. This is also given. So once we substitute these values, 0.01296, which we have calculated just now here, this value here, 0.01296, humidity at the dry bulb temperature. And this is the humidity at the wet bulb temperature. We have to find that out. And this is the dry bulb temperature, and this is the wet bulb temperature here. And this is the value of CP, and this is the value of lambda is given. And if we just see that these will cancel out. Okay, this the left hand side and the right hand side are dimensionally consistent. You can see that. So this is the equation we get, that these are the values here. You look into our website, and it gives you a little more details here. So if you put this equation, the right hand side should be equal to this particular value here. So how do you do that? In this equation, what we do, we first assume a wet bulb temperature, and at the wet bulb temperature, we find out what is the saturation pressure, that is the vapor pressure, at the wet bulb temperature. So once we know that, from there we should be able to calculate the saturation humidity, which is the humidity at the wet bulb temperature. Okay. So first we assume this one, and based on that, and using the value of saturation pressure, which is given in the table, which the data is supplied to us, so we should be able to calculate the humidity at the wet bulb temperature. So, and then we calculate the left hand side. If this left hand side, the value is equal to this one, then we say this is the correct assumption. Otherwise, we have to make other assumptions. Okay. So this is a very important equation. Now let's discuss option A. Option A is wet bulb temperature. Wet bulb temperature 284 Kelvin? Let's look here. This is my option A. This is not possible. Why? Because you see, we have seen that this air, which is a dry bulb temperature of 310 Kelvin, uh, partial pressure of water vapor is 1.28 kilopascals. Where have we seen that? Right here. Partial pressure of water vapor at this 310 Kelvin dry bulb temperature is 1.28 kilopascals. Now, if we look in the table, given table, here we see that at 284 K, that the vapor pressure, the saturation pressure is 1.28 kilopascals. So therefore, what it means is here, this is the air which has a partial pressure of water at 1.28 kilopascals, and this dry bulb temperature is 310 Kelvin. But this is saturation pressure is 1.28 kilopascals at a temperature of 284 Kelvin, which is approximately 11 degrees Celsius. So as we can see, for this humidity, partial pressure water vapor, the dew point is 11 degrees Celsius, because at this 284 K or 11 degrees Celsius, the saturation pressure is equal to 1.28 kilopascals. For understanding this one, please read the standard textbook or your lecture notes. Dry bulb temperature is 310 K, and we have seen this dew point temperature is 11 degrees Celsius. Now, for any relative humidity less than 100%, we'll see that the dew point temperature would be lower than the wet bulb temperature, and this wet bulb temperature would be lower than the dry bulb temperature. This is 310 Kelvin is okay, and this is 11 degrees Celsius, which is equal to 284 Kelvin. So the wet bulb temperature cannot be 284 Kelvin. It has to be higher than 284 Kelvin. So this option A is not correct. And this, of course, could also be proven by using this particular equation, which, of course, is shown in detail in the website. Now, for option B, uh, what is the option? That's the wet bulb temperature is 294 Kelvin, which is 21 degrees Celsius. Is this the correct option? Let's see. First, we find out the partial pressure of water at this wet bulb temperature 294 Kelvin. But you can see that you can see that when this week here, in this week, at the wet bulb temperature, the air near this week is saturated. So this would be the saturation. The partial pressure of water would be equal to the saturation pressure at the wet bulb temperature, right? So we have to first find out what is the saturation pressure at 294 Kelvin. And if we go to the table, we'll find out at 294 Kelvin, the saturation pressure is 2.50 kilopascals. Let's look at it. At 294 Kelvin, the saturation pressure, the vapor pressure is 2.50 kilopascals. That's already given. So if we go there, If we substitute these values, 2.50 kilopascals, the total pressure is 100 kilopascals, we see that's a humidity. Okay, so that's a saturation humidity, right? Because that if this at wet bulb temperature, this would be the saturation humidity. So if we substitute in this equation, the details is shown. You will see that you substitute this value. This already is given. We calculate this. Calculated this humidity at saturation humidity at 294 Kelvin, which is 0.02564 molar saturation humidity. We substitute here. This is the dry bulb temperature, and this is the wet bulb temperature, which is option B. We see this value comes to be equal to this. So this is very much close to this particular value. So we can say this left hand side is equal right hand side. So option B is correct. More details, of course, are shown in the website here. All right. Now let's look at option C. Now, option C is 310 Kelvin, which is the dry bulb temperature. As we said, only for a relative humidity of 100%, the dew point temperature would be equal to the wet bulb temperature, would be equal to the dry bulb temperature. But for us, the relative humidity is 20%. So the wet bulb temperature cannot be equal to the dry bulb. This is 310 Kelvin. So this wet bulb temperature cannot be 310 Kelvin. So this option is wrong. Option C is wrong. Option D is 321 Kelvin, so which is higher than the dry bulb temperature. That, of course, is not possible because that will violate the second law of thermodynamics. So option A we have seen is not correct. Option B is true. Option C is not correct, as we've seen here, and option D is also not correct. Okay, so the correct option is, of course, B. B is the correct option. That is 294 Kelvin, is the correct wet bulb temperature. Now let's look at the practical application of this problem. Okay, before that, we can solve this problem. This option B, we can show that that is the correct option using psychrometric charts. It's very easy. I will show you how to do that. So this is the dry bulb temperature here, 310 Kelvin, which is 37 degrees Celsius. This is 37 degrees Celsius. So you go straight up and you find out the 20% relative humidity line. You see this is 30%, this is 40%, this is 50%, and this is 100% relative humidity line here. So we take this 20% line here and we draw like here. So this is the intersection point. So from here, you can directly read what's the value of the humidity at this point, which you will see, which is shown in the website. We have done the calculation. This is the mass humidity. Remember mass humidity? That means it's kilogram of water vapor per kilogram of dry air. So that can be directly read from here. And now to find out the wet bulb temperature, we follow the constant wet bulb line here, which of course is the constant enthalpy or the constant adiabatic saturation line, which is basically from here, we go all the way up to the 100% humidity, relative humidity line here. And then we come down here to read what is the wet bulb temperature. See, that's 21 degrees Celsius. Okay, that's the answer what we got, which is option B. Okay. Also, if you want to see what is the dew point temperature, what you do from here, you go straight out here at the same humidity. You just go up to 100% line here. This is my 100% line here, and you come down here and read the temperature. So that's 11 degrees Celsius. So if you know the dry bulb temperature, if you know the relative humidity, you find out this intersection here. This is the dry bulb temperature. This is the intersection here. If you go right here, you find out the mass humidity. If you go follow the constant enthalpy line and hit the 100% adiabatic saturation line, from here you can read the wet bulb temperature. And if you go horizontally up to the 100% line, you can read the dew point temperature here. Okay. Remember, this is for 100 kilopascal in our problem, but this the chart has been drawn for 1 atmosphere, 101.325 kilopascals. Okay. Again, from here we can see option B is correct. Now, what's the practical application of this problem? There's a lot of application of this problem. One of the standard one is, of course, cooling tower design and operation. What's the cooling tower? Um, uh, so this is very much an industrial cooling tower, and this is a schematic diagram here. So what it does, hot water from heat exchangers, pick up heat from, let's say, exothermic reactors, distillation column condensers, etc. And so this heat exchanger, let's say, are cooled by water. So the water picks up the heat from these units and therefore becomes heated. So let's say they come out at 40 degrees Celsius, 45 degrees Celsius, whatever. Okay, so we cannot keep on rejecting this water at a higher temperature to any river or to any surface water. So what they do, they just trickle down this water here, and there's a suction of air. So these are fans. So there's a suction of air here. And what this happens is that in a cooling tower, hot water is cooled by contact with water. A part of the water evaporates, and this evaporation, that as this evaporates, of course, it has to take the latent heat, and it takes the latent heat from the rest of the water, and therefore the rest of the water becomes cooled. So, and this is then again sent back to the process units or the heat exchangers for picking up heat. The lowest temperature to which the water can be theoretically cooled, of course, is called the wet bulb temperature. So this is an industrial cooling tower. And as you can see, the hot water is sprinkled from the top. And these are here the packings right here inside. And there's, of course, suction of air. And the water falls down, and as I said, as it falls down, there's evaporation, and the rest of the water cools down. So this is a tray where the cold water is collected, and this is then sent back to the process unit again, and this again gets heated up and comes back here. Okay, there will be some amount of makeup water that has to be added. Uh, of course, this is the lowest temperature that can be achieved is the wet bulb temperature. So that's why knowing the wet bulb temperature is so important, which depends upon, of course, on the relative humidity of the ambient air, okay, and the dry bulb temperature. Approach, there's something called an approach. The approach is the actual temperature, which it will come out minus the wet bulb temperature. Of course, it cannot, the theoretical lowest temperature is this one, but we have to design the system for an approach temperature. Okay, so again, there are a lot of discussions in the standard textbooks. Also, in drying of solids, as for example, fertilizer granules, in constant rate period, the surface temperature of wet solids is wet bulb temperature. Again, there are a lot of theoretical models based on wet bulb temperatures, how to dry the solids. In spray drying, droplet surface temperature again can also be again assumed to wet bulb temperatures, and spray dryers are also extremely used in different process units. So this is a kind of a long answer for this problem. Anyway, the final correct option is option B, which is 294 Kelvin.